Good day, everyone. We are here to give a presentation and to look into self-potential methods in geology. We will also be uncovering the underlying properties and principles and exploring the practical side from the parameters we measure to the equipment we use. We will also get a sense of how SP methods are applied in the real world and what the results can actually look like. I am Crystal May Ambatang, and together with me are my esteemed colleagues, Mr. Langag, Ms. Maganon, Ms. Taidak, Ms. Balanci, and Ms. Fabros. According to US EPA 2024, the self-potential method, also known as spontaneous potential, is a passive geophysical technique that measures naturally occurring electrical potentials in the Earth's subsurface. These potentials arise due to electrokinetic and electrochemical processes such as groundwater flow through porous media and interactions between pore fluids and minerals. By measuring these natural voltage differences, the SP method can provide insights into subsurface features and processes. Imagine the ground has its own weak natural electricity. So the SP method is like using a special tool to measure these tiny underground electrical signals without digging. These signals happen because of things like water moving through the ground or how water reacts with rocks. So by measuring these natural electrical differences on the surface, we can get hints about what's happening underground, like where water is flowing or if there are certain materials hidden there. It's like listening to the Earth's quiet electrical buzz to learn about what's beneath our feet. The self-potential methods, or the SP method, was devised in 1830 by Robert Fox, who used copper plate electrodes connected to a galvanometer to detect underground copper sulfide deposits in Cornwall, England. So this is the copper plate on the left side, or this first picture, and the second picture is the galvanometer. So the copper plate is like the feelers or the points of contact with the ground, and the galvanometer, this was the detector or the meter that showed if any electricity was flowing in the wire connecting the two plates.
Controlling property of self-potential method. What is controlling property? This refers to the physical characteristic of a material or environment that directly influences how a geophysical method works or what it measures. In the context of geophysical methods like the self-potential method, the controlling property is the natural electric potential differences in the ground caused by physical or chemical process such as fluid flow, redox reactions, or temperature differences. So, for the self-potential, the controlling property is a source of the natural electrical signal that this method detects. Understanding this helps scientists to know what kind of subsurface features the method can reveal. The self-potential method is controlled mainly by three natural phenomena. First, we have electrochemical processes. These occur due to the redox reaction, particularly around ore bodies. When minerals like sulfides undergo oxidation or reduction, they generate electric currents which result in measurable voltage differences at the surface. Next, we have electrokinetic or streaming potentials. This is when underground water flows through porous rock or soil. It drags along ions, creating an electric field. This movement generates voltage differences that reflect the direction of intensity of subsurface water flow. And lastly, we have thermoelectric effects. Temperature gradients underground can also cause voltage differences due to the Seebeck effect, where heat causes electrons to move from hot areas to cooler ones, producing small electric currents. These natural electric signals can reveal important underground features like water pathways, mineral deposits, and geothermal activity zones. Because the self-potential method is passive and non-invasive, it's a valuable tool in environmental studies, mineral exploration, and underground water researches.
Let's move on to the principles of SP methods. Self-potential or spontaneous polarization method is based on the surface measurement of natural potentials resulting from electrochemical reactions in the subsurface. It does not require electric currents to be injected into the ground as in the resistivity and IP methods. The SP method ranks as the cheapest method of surface geophysical methods in terms of equipment necessary and amongst the simplest to operate in the field. So this method of prospecting is based on the measurement of the electrical potentials naturally present in the earth. This method is also known as the spontaneous polarization method or implied as the SP method. Several sulfide ores like pyrite, pyrrhotite, chalcopyrite, molybdenite, and others show spontaneous polarization. Anthracite and graphite are known to give strong SP effects. So the conditions that led to the development of self-potential are shown in the next slides with reference a sulfide body. The figure shows the occurrence of oxidation at the top and reduction at the bottom in a subsurface sulfide or body which is in the zone of aeration and also in the zone of saturation. As a consequence of this, the negative VE charges develop at the top and the positive VE charges at the bottom, and the current flows from top to bottom within the body and back to the top outside of the body. It means SP loss occurs on the ground above the ore body. Imagine you're walking across the ground. Underneath, there's a layer where the ground is dry, which is the zone of aeration, and then a layer where the ground is soaked with water, which is the zone of saturation, also called the water table level. Buried within this wet zone, there's a sulfide or a chalcopyrite ore body. This is a deposit of minerals that can conduct electricity. Now, look at the arrows. Near the top of the ore body, something called oxidation is happening. This is like a chemical reaction where the minerals are losing electrons. At the bottom of the ore body, reduction is happening where the minerals are gaining electrons. So this movement of electrons creates a natural electrical current flowing through the ground, shown by the curved lines with rows. So these electrical currents spread out and reach the surface. The graph at the top shows what a scientist might measure on surface using a special equipment. So the y-axis shows the millivolta, a unit of electrical potential. Notice how the readings dip down to a low point right above where the ore body is buried, around points B and C. As you move away from the ore body towards point A and E, the readings go back up. So the self-potentials also develop due to filtration and diffusion absorption activities. But the potentials are weak and do not exceed a few tens of millivolts. So these are helpful in locating leakage from reservoirs. The SP method relies on the measurements of naturally occurring electrical potentials that arise from various mechanisms, including the three of the following: electrochemical potentials, electrokinetic potentials, and thermoelectric potentials. So when we say electrochemical potentials, these arise from ion transport across interfaces like those between minerals and groundwater. For electrokinetic potentials, these are generated by the movement of charged ions in fluids relative to the stationary rock. And lastly, thermoelectric potentials are related to temperature gradients in the subsurface.
Parameters of SP method. The primary parameters measured and analysis in self-potential methods are: number 1, self-potential, voltage or potential difference. This is the fundamental measurement. SP surveys involve measuring the natural electrical potential difference between two non-polarizing electrodes planted in the ground and different locations. The unit of measurement is typically millivolt. Number 2 is spatial location. survey station coordinates. The voltage measurements are always recorded along with the precise location. Example, nothing testing elevation of each electrode pair. This allows for the creation of potential map and profile that show how the SP value vary spatially. Number 3, polarity. The direction of the potential difference, positive or negative. Number 4, amplitude. The magnitude of the potential difference, usually measured in millivolts. Number 5, shape of anomalies. The spatial distribution of potential variation can provide clues about subsurface features. Number 6, data resolution. The spatial resolution of the SP data depends on the electrode spacing and survey configuration. Number 7, depth of investigation. The SP method is generally sensitive to features within a few tens of meters depth. The SP method typically measured potential difference between electrodes placed at the surface or within boreholes.
Moving on to the methods of self-potential lows. There are three methods of locating SP lows in negative centers. They are, first, by tracing equipotential lines directly on the ground. It's like drawing lines on the ground where the electricity level is the same. So following these lines helps you find the low spots. Second is by determining the potentials on a grid of stations and drawing in planned equipotential lines, like measuring the electricity level in main spots and then drawing lines on a map to show the low areas. And lastly, by determining the potential gradients. It's like checking how quickly the electricity level changes as you move around to find the lowest points.
Equipment for SP surveys. These are the instruments required for carrying out SP survey. One is a pair of non-polarizing electrodes. These are special electrodes that don't interface with natural voltage in the soil. One is fixed in one spot, called the reference electrode, and the other one moves around to different location, called the moving electrode. 2. A DC potentiometer or a voltmeter. This device measures the tiny voltage differences between the two electrodes. 3. Reference and moving electrodes. Example, you leave one electrode in one spot. That's your reference. It's like your home base. Then you take another one, the moving electrode, and walk in it to different places to measure how the natural electrical voltage changes across the area. These voltage changes can tell you a lot about what's happening underground, like where water is flowing or where geothermal activity might be. 4. Isolated connecting wire. These are the long flexible cables that connect your electrodes to the voltmeter, the device that reads the voltage. They need to be isolated so they don't pick up interference, and low resistance so your signal stay clean and strong. In practice, they can be really long, up to 500 meters, so you can move around without dragging your entire setup with you. 5. Measuring tape or GPS. Now you need to know where you took each reading. That's where either measuring tape if it is a small area or GPS for larger or more rugged terrain come in. GPS makes life a lot easier by pointing the location for every voltage reading. Data logger or notebook. This is where the human touch come in, or a digital one. You or your device will log the voltage values, the locations, and any observations. For example, if the ground is wet or there's unusual terrain, those can help explain unusual reading later. Example of this, you and a friend are trying to find out where water flows underground. One friend stays still with a sensor and you walk around with another one. You both stay connected by a long cable and every time you stop, you you wire down the signal. You're getting and where you are. When you go back and plant those numbers on a map, patterns start to emerge, maybe showing a stream underground or geothermal hotspot.
As Mr. Langag said, this is a typical configuration for a self-potential survey, with a base electrode used as the reference and a roving electrode for the field measurements. So the cable can be 500 meter long, and a GPS or a global positioning system is used to measure the position of the stations where the self-potential is measured.
Okay, let's move on to the application of the self-potential method. The self-potential method or SP method is a geophysical technique that measures natural electrical signals in the ground without using any external power. These signals are caused by flowing water or chemical reactions underground. The applications are: number 1, groundwater exploration. Helps find underground water by detecting electric signals from moving water. Number 2, mineral exploration. Used to locate minerals deposits, especially sulfide ores, which produce natural signals when they react with air or water. Number 2, volcano and geothermal studies. Detects hot water movement and heat sources below the surface. Environmental studies. Tracks pollution in groundwater and leakage from landfills. Engineering investigations. Find water leakage in structures like dams or embankments.
We have a sample results of SP method, which is a field setup of waterborne SP data collection by Icart et al. 2018, wherein it shows the typical flow conditions during measurements. It has the GPS receiver, data logging multimeter, and a 2-meter long electrodes. This graph shows the SP results from waterborne survey as researched by Icart et al. 2018.
Sample results of self-potential methods. Number 1, groundwater exploration. Recharge-discharge zones, and the location is semi-arid area with fractured bedrocks. SP results, background, SP 0 to -50 MV. Anomaly zone, -150 to -300 MV over a narrow bands. Interpretation, negative SP anomaly corresponds to recharge zones where water flows downwards through fractures. Streaming potential occurs when water drags excess charge through pollutes methods, permeability and recharge rates. And the used, delineating well sites or mapping subsurface flow paths. And for the number 2, mineral exploration, sulfide ore detector. The location is volcanogenic massive sulfide deposit area. And the SP results, large negative anomaly, -400 to -600 MV. Anomaly center above the known ore body. Symmetric profile often resembling a dip or true. And for the interpretation, caused by electrochemical reactions between sulfide minerals. For example, pyrite, chalcopyrite, and surrounding ground floor. Act like a natural battery with redox reactions generating electric potential. SP profile often correlates with depth, size, and types of ore body. And for the used, collating concealed sulfide mineralization. Cost-effective exploration tools when combined with resistivity or IP surveys. And for the number 3, environmental application, landfill or leachate detector. The location is municipal landfill over unconfined aquifer. And the SP results is positive anomaly. Positive 100 to positive 250 MV near the center of the landfill. Gradual decay of potential with distance. And for the interpretation, positive SP due to electrokinetic effect from leached plumb migration. Conductive fluids in the unsaturated zone generate current as they flow, modifying the natural potential. SP, frigid show directions and intents of contaminating flow. And for the use, monitoring lake sheet movement, non-invasive long-term site surveillance. And for the number 4, geothermal or volcanic area, subsurface fluid movements. The location is geothermal field with active hot springs. And for the SP results, complex pattern of anomalies from negative 200 MB to positive 300 MB. High positive SP around hot spring outlets. And for the interpretation, positive SP caused by upward movements of thermal fluids, especially in fractured zones, combines of electrokinetic and thermoelectric effects. Mapping helps identify productive zones or fracture permeability. And for the use, assessing reservoirs structure, locating drilling targets for geothermal energy.
That's all. Thank you for listening.